Okay, so today is all about getting you ready for Riemann sums. Riemann sums is the next big thing that's going to come after you get an intro to antiderivatives. So Riemann sums is the way we estimate the area underneath curves. And we'd have a curve and we divide a certain interval into subintervals. And then what we do is we pick either the left endpoint, the right endpoint, or the midpoint, and we draw rectangles. And we add up the area of the rectangles, and that's how we estimate the area under a curve. And we're going to increase the number of rectangles. So there's a lot of adding to do. We add up a whole bunch of areas. So we like to use shortcuts, which is the sigma or summation notation. So you may or may not have seen it ever before. This big sigma just means add up a bunch of numbers. It stands for sum, S for sum. We start with an index at the bottom. This gives us our starting point is at the bottom. And then we have an ending point at the top. So n equals 1, we'll say 5. This would be our ending point. And then we'll have a function in here that we're adding up. So we'll start with something really simple. If we just had the sum as n equals 1 to 4, like it has right there on the example of n. So n is 1, and then 2, and then 3, and then 4. And we just add those numbers up. So we'll go through a few examples. If you are asked to write a summation that will give you the sum of the first 10 positive integers. Well, this variable here is not important. It can be any variable that you want it to be. So I'm going to call it K this time just to be different. We want the first 10 positive integers, so we can go from 1 to 10, and that's just K. So that would give us 1 plus 2 plus 3, all the way up to 10. Now, we're same as the letter that you use to represent the index isn't important. Your starting point is up to you too. So if I wanted the first 10 positive integers, I could let my starting point be 0. Then my ending point would be 9, but I would need to type in K plus 1 for my function. And that would give me, when K is equal to 0, you'd get 0 plus 1. 0 or 1 plus 1, 2 plus 1, all the way up to 9 plus 1. So that's just another way of writing the same summation. If you wanted to have your K start at 2, then you could go to 8 and it would be K and minus 1. So when K is equal to 2, you'd have 2 minus 1, and that wouldn't be 8. It would be 11 because you wanted to add up 1, 2, all the way up to 10. So you can have your starting point anywhere you want it to be. You just have to make sure that you're getting what you want when everything is added up. If we wanted the sum of I squared from 1 to 6, we go 1 to 6, and we just put I squared for our function. Easy enough. If we wanted the sum of 1 over 1 plus 1 over 2 plus 1 over 3, we could let x start at 1, go all the way up to 50 of 1 over x. That would give us 1 over 1 plus 1 over 2, all the way up to 1 over 50. So you can see why it's really handy, because I didn't even want to write down 10 digits. I definitely don't want to write down 50 fractions. So it's a nice way of shortcutting a big, long sum of numbers. If you want some more info, you can go to Paul's online notes. Math is Fun and Math Center also had a really good explanation of sigma notation. Any questions? Cool. So let's next talk about intervals. And subintervals, because we'll be taking an interval and dividing it up into pieces, and we want a way to represent the left endpoints, the right endpoints, and the midpoints of those intervals, and to determine where they are. So we want to take the interval from A to B and divide it into n subintervals. And then we're going to want to know what the left endpoints, the midpoints, and the right endpoints are. So first thing we do is determine the width of each of the subintervals, and we call that delta x. And delta x is equal to b minus a, the length of the interval, divided by the number of subintervals. So thinking back to our little curve where we were going to take this interval and divide it into subintervals, and we're going to pretend that my subintervals are all the same width, that each one would be delta x wide. So our goal for Riemann sums will be to find the area of each rectangle. I'm going to draw in these rectangles whose height is equal to my left endpoint. So I need a convenient way of determining each of these left endpoints. Well, your left endpoints are always going to start with the starting point of your interval, A. So it starts with A, and then you add a delta x, and then you add another delta x, and then you add another delta x, until you've added n minus 1 delta x's. So here I have divided it into 1, 2, 3, 4, 5 intervals. My first left endpoint is A plus delta x, A plus 2 delta x's, A plus 3 delta x's, and then my final left endpoint is A plus 4 delta x's. My n was 5, so I add 4 n minus 1 delta x's for my left endpoints. Right endpoints, see if I can make 5 sections again. So we have 1, 2, 3, 4, 5. This is A, and this is B. If we want right endpoints, then the first one is A plus 1 delta x, and then A plus 2 delta x's, A plus 3 delta x's, A plus 4 delta x's, and finally B, which is A plus n delta x's. So right endpoints always start 1 delta x to the right of A, and then you add, and then you add until you get all the way to n delta x's, and you end up at the right end of your original interval. Midpoint's a little trickier. Still going from A to B. Delta x is still B minus A over n. But this time, we want to locate the middle of each of these intervals. And that's where we would draw our rectangles. So instead of starting at A or at A plus delta x for midpoints, we start half of delta x to the right of A. So A plus 1/2 of delta x. But then after that, to get to the next midpoint, we add delta x, we add delta x, we add, and we add. So A plus 3/2 of delta x, and then A plus 5/2 of delta x, all the way to A plus n minus 1/2 times delta x. So you'll end up 1/2 to the left, kind of splitting the difference there. Now let's put some real live numbers in there. If we want to divide the interval from 2 to 7 into 10 subintervals, first thing we do is calculate delta x. So 2 is A, 7 is B, and 10 is n. 7 minus 2 over 10 equals 5 over 10, which is 1/2. Left, right, mid. See if I can fit them all on one page here. So my starting point for my left endpoints is going to be A, 2. Then I add 1/2. Then I add another half. I add another half. And I do this 1, 2, 3, 4, 5, 6, 7, 8. So here's my first left end point, and I have my 10 left end points, and I'm delta X away from B. My right end points, they just kind of shift up one. So I start at 2.5, 3, 3.5, 4, 4.5, 5, 5.5. And I end up at B, which is 7. Midpoints is where the arithmetic's a little trickier. We start 1/2 of delta X away from 2. So 2 1/4. And then 10 times we add. So we add 2/4 gives me 2 3/4. 3 1/4. 3 3/4. And we have ended up 1/2 of delta X from B. Here we've ended up delta X from B. Easy enough? Okay. I'm going to do an example with pies in it because you know that we're not going to get away from trig. Here's my pretty little picture that I created with a number line from 2 to 7, showing my right endpoints, my left endpoints, and my midpoints. Everything works exactly the way you want it to. So if we wanted to go from 0 to 2 pi with 8 subintervals, then our delta X would be equal to 2 pi minus 0, B minus A divided by N. So pi over 4. Our left endpoints, we start at 0. And we just add pi over 4 each time. So you can see where a sigma is going to work well for adding these things up because we use a pattern. We increment by delta X each time. One more delta X gives me pi halves, another delta X, another delta X, another delta X, and let's see, pi, 5 pi over 4, then 3 pi over 2, and then 7 pi over 4. 1, 2, 3, 4, 5, 6, 7, 8 left end points. Right end points, we start at the pi over 4, pi over 2. We keep going and we end up all the way around the unit circle at 2 pi. Midpoints, we start halfway between. So we start at pi over 8, but we still increment by delta X, which is pi over 4. So I have to add 2 pi over 8. So I get 3 pi over 8, 5 pi over 8, 7 pi over 8, 9 pi over 8, 11 pi over 8. Let's see, here's 1, 2, 3, 4, 5, 6, 7, 8. And you can see I'm pi over 8 away from 2 pi. So half of delta x from 2 pi. So we'll be plugging these numbers in because that's how we'll calculate the height of our rectangle when we're trying to find the area of a bunch of rectangles that live beneath a function. So my midpoints, I'll be calculating my function's value at this midpoint and that midpoint and that midpoint and that midpoint, and then I'll multiply each by delta x to get the area of each of these rectangles. And then we add them all up and it gives us an estimate for the area underneath the curve. And that's the whole goal of the first section of that next chapter that you're starting. Questions so far? Yes.
When you're doing overestimating and underestimating for the midpoints, that's supposed to average it out, or is that because you'd be like, say if it goes increasing and it's from overestimating to underestimating, how would that work?
Yeah, the midpoint is going to give you the best estimate as a general rule. If you have a function that's increasing, then your left endpoint is going to give you an underestimate. And your right endpoint would give you an overestimate. So your midpoints would do exactly what you said. It would even that out. If you have a decreasing function, then it works backwards. Your left endpoints will overestimate. Your right endpoints will underestimate, and your midpoints will give you the best estimate. If your function changes, then you can't make a prediction whether you've got an overestimate or an underestimate.
Will it ever get to a point where we can do that with the changing in slopes?
What we do is we take the limit as n approaches infinity, where we do the sum of n rectangles. And you will learn to do what's called an integral, and the fundamental theorem of calculus teaches us how to calculate that. So you'll be able to eventually figure out the exact area underneath those curves. You won't have to estimate anymore.
Okay.
That's when it gets fun, is when you get to the fundamental theorem of calculus. But first you have to get through the Riemann sums and be able to estimate it. And the next thing I'm going to do is teach you how to do that using your calculator. So grab your calculator so we can play together. And I did lots of screenshots on here. So as we go through, if you get kind of lost, you'll be able to go back and look over this sheet. And let me write down the first one I was going to do. I have the function f of x is equal to x squared plus 3x minus 1. I want to take the interval from 2 to 7, which we just did, divide it into 10 subintervals. And first I'm going to show you how to just do the sum as n goes from 1 to 10, because we're adding up those 10 subintervals of this function evaluated at the left endpoints. So this, what I have written here so far, is not an estimate of the area under the curve. If you wanted an estimate of the area under the curve, you would have to have f evaluated at the left endpoints times delta x, because that would be the height of your rectangle, and then delta x is the width of your rectangle. But let's just learn how to use the calculator first. So we'll start with this slightly simpler thing. Do the sum as n goes from 1 to 10 of f evaluated at the left endpoints. So first thing we need to do is to get our function into our calculator. So turn it on, hit table, edit function, get rid of that old function, and put in x squared plus 3x minus 1. Hit enter. You're going to be on the next screen. You can't go directly to doing your sums. You have to hit second quit and get out of there. So you have to exit the table screen. Then you're going to press the math button. It lives right here below mode. And you can see a bunch of stuff here. You can either press 5 or you can arrow down until you see sum, because that's what we want, is the sum. And it looks just like that little sigma. We're always going to start at 1. We're always going to end at the number of rectangles, or subintervals. So far, so good?
Yeah.
Okay. Stop me if I go too fast, because I can't watch your fingers to make sure that we're on the same page. So now we need f of. To get f of, you just press table, enter. And you should have f with a parenthesis there. Now I want left endpoints. I always start at A. My A in this case is 2. Plus, then I write down delta x. So left endpoints, it's A plus delta x times x minus 1, because my counter, my x, is starting at 1, but for left endpoints, I want to start out not adding any delta x's. I want to start out just at A, so I'm going to do delta x times x minus 1. My delta x in this case was a half. I like to use a fraction. If you're a big fan of the decimal, you could use 0.5 if you want. Open up a set of parentheses, x minus 1. Close the x minus 1 parentheses, close the f of x parentheses. One reason I like to use the fraction is that it makes this parenthesis a different size than this one, and it helps me to remember to close them both. If you don't close them both, the calculator's going to get angry and give you an error message, and you're going to get frustrated. Then you hit enter. And it adds all those numbers up for you, as if by magic. Did you make it through that?
Yeah.
Cool. Okay, so that was left endpoints. If I wanted midpoints, I want to start half of delta x away from A. So my input would need to be A plus delta x times x minus 1/2, because my counter is starting at 1. So if I do 1 minus 1/2, then I'll have 1/2 times delta x plus 3/2 times delta x plus 4/2, 5/2 times delta x, etc. So, being the lazy person that I am and prone to making mistakes, if I had to retype all this, I just arrow up twice, I hit enter, and then I can arrow over here to my 1, press that fraction button, and change it to 1/2. Now I've added up all the midpoints. What if I wanted right endpoints? Well, if I wanted right endpoints, I want A times delta x just times x, because I want to add in delta x's. I want to add delta x and then 2 delta x's, 3 delta x's, all the way up to n. So I have a choice. I could go in here and I could delete stuff. Delete, delete. I could change that to a 0, or I could just keep deleting until it was just x sitting there. Either way you want to do it, you can just edit it and get it in there. You have an insert and a delete button. So if you leave something out, you can always press second insert, and it allows you to go back and add something in. If you want to get rid of something, you press the delete button. So let me go up, because the guy this morning was very impressed that we could insert stuff. So let me show you how to do that. Suppose I wanted to add something in here if I had left out the 1/2. So let's delete it, delete, delete. I have this in here and I think, oh crap, I left out the 1/2. I press second insert, and now I can put it in there.
I get 15/15 over 4.
Cool. I think that's the same thing I had.
Okay.
Yeah. 15/15 over 4. Yep. Okay. So let's try the next one, which was our trig function. And I chose this one for a reason, because we have cosine squared of x minus x. And when you see it written down, it looks like cosine squared of x minus x. But when you put that function into the calculator, table, edit function, clear out the old stuff. You can't type it in like that. You have to open up some parentheses, put them around cosine of x, and then square on the outside. Yeah. Question?
What were you supposed to do with the left midpoint and right midpoints after you find those numbers? Do you add them and then divide by 3?
All I was doing so far was just adding them up. Now, if you wanted to find the area of the rectangles, if we wanted to estimate the area underneath the rectangles, I'll do that with this one. I'll go through the whole thing and show you how to estimate the area under the rectangle for them.
Okay, thank you.
Sure. So let's go ahead and get this put in here. We have cosine, open up parentheses, make sure you're in radian mode, cosine of x, close the x parenthesis, close the cosine of x parenthesis, and square it, and then subtract x. Hit enter, and then quit. Hit the math button, and I just hit 5. So I want n is equal to 8, delta x was equal to pi over 4, and we're going from 0 to 2 pi. And let's go ahead and estimate the area underneath that curve. And we're going to estimate it using my left endpoint. So I will need the sum as x goes from 1 to 8. This is always the number of rectangles. F of my starting point. Well, 0 is my favorite starting point because I can ignore it. I don't have to put 0 plus pi over 4 times x minus 1. I can just put f of pi over 4 times x minus 1. That's the nice thing about having my starting point be 0. So this is the height of my rectangle. Then I would need to multiply this by pi over 4, which would be the width of my rectangle. And not pi over pi, but pi over 4. So we're going to go from 1 to 8. F of, so table, enter, 0 plus, don't have to put that down, so that's one less place for me to make a mistake. Delta x, which is pi over 4 times x minus 1, because I'm starting with left rectangles, and I close my f of parentheses. Again, I say it out loud every time I do it so I don't forget. Close the x minus parentheses, close the f of parentheses. Then I'm going to multiply that, not add, but multiply. Whoops. Multiply that by delta x, pi over 4. And that gives me an estimate for the area underneath that curve. Easy enough to go back and estimate it with midpoints.
I get a syntax error for the how many give me a second.
Okay.
How many parentheses do you have after the -1?
Let's see. I have x minus 1, and then I have another parenthesis. So there's 2 parentheses after that.
And you just do times multiply pi over 4, correct? And then end that parenthesis, correct?
Yeah.
Right, what am I doing wrong?
I would start over.
Okay.
Because usually if you've gotten into a parenthesis problem, it's better to just start over rather than to try to fix it. So let's go through the whole thing again. Press your math button. 5. You're going from 1 to 8. F of, so table, enter. Fraction button, pi over 4. Open up a set of parentheses, x minus 1, close x minus 1's parentheses, close the f parentheses, times fraction pi over 4. Now you don't have to close that next set of parentheses because your calculator has done that automatically for you. Did it work that time?
Yeah, it did. Sorry.
Awesome. So now that you've got it, you can go up here, arrow over, change that 1 to a 1/2, and get your midpoint estimate. You can go up. I'm just going to delete. Oops, it deleted the wrong direction, so I need my X back. Delete, delete, delete. So now I just have pi over 4 times x. And there is my right-hand estimate.
For the midpoint, you got -16, correct? With a list of numbers?
Yes.
Okay.
Now, one good way you can check to see if you're close, what we're actually estimating here is an integral. And you actually have an integral button there on your calculator. Well, I have to get down below everything. Second, this is what we are estimating. We are estimating the integral from 0 to 2 pi. Of our function. So instead of typing the function in again, I'm going to be super lazy and just do f of x. And your calculator doesn't know how to do calculus, it just does an estimate too. So our midpoint estimate was pretty darned close. Questions?
So the integral is the area of that?
It's the area under the curve, yes.
Okay.
Yeah, I'm not supposed to tell you that yet because I'm not supposed to teach you calculus, but yeah, you're going to learn that soon. The integral is the area under the curve.
Okay.
Yep. Which is the whole goal of the Riemann sum, is to estimate that area. So we think of it as we find the area of all those little rectangles. The more rectangles we have, the better our estimate. So we take the limit as the number of rectangles goes to infinity.
So when we're doing the left hand and the right hand of the points, those are just trying to get us to the average, but when we do the midpoints, that's what we're looking for, correct?
Well, it's not always going to, they're just different ways of doing it. You could pick any point in those rectangles that you wanted to. The point is that you're going to let the number of rectangles approach infinity. So as you get to infinity, the left endpoint, the right endpoint, and the midpoint are all the same.
Okay.
So don't get too hung up on which point you're using. Just use the point that you're told to use, basically. They're all just estimates. Usually midpoint gives you the best estimate, but they're all just estimates.
Okay.
Feel a little better about it now?
Yeah.
Okay. I think you'll find your Riemann sums and stuff a whole lot easier after having gone through this.